Welcome to the lecture on page management. So we will focus on two important topics. One is reverse mapping, which is given a physical page. How do I find out all the virtual pages that are mapped to it? And these virtual pages will be pages across processes. And the other is the multi-generational LRU, the MG-LRU replacement algorithm that Linux uses. So the background that we need for understanding replacement is a data structure called a Bloom filter and the notion of reverse mapping, which we will anyway cover. So a Bloom filter is used for set membership in the sense that if there is a set S, you want to know if an item is an element of S or not. The Bloom filter is a probabilistic data structure in the sense that, so it will return a yes or no. The yes cannot be trusted. If it says yes, it may not be there. There is a probability, which means false positives are allowed. But if it says no, it is definitely not there, which means false negatives are not allowed. So, false positives are sadly allowed. False negatives not allowed. All right, so far so good. So how does this really work? The way that this works is we have a large bit vector of m bits. Given a key, we use 4 separate hash functions. So the key is this item. Given a key, I use 4 separate hash functions to map it to 4 distinct locations on this m bit vector. Correct? 4 hash functions, 4 locations. In all 4 locations, I set the bit from 0 to 1. If it's already 1, I don't do anything. In case it is 0, I convert the bit from 0 to 1 in all 4 locations. All right. Now, if I want to test if, let's say, a certain key k dash is part of the set or not, then I again hash it with these 4 hash functions, which actually takes me to 4 locations in the bit vector. If all 4 locations are 1, I can say that the key is probably there. Why probably? Because 2 different keys can have, one key could have these locations, one more key could have these locations. Then what will happen is that k dash and k double dash are there, but k is not there. Right? Key k is not there. So then the 4 entries will still be 1, but they will not be 1 because of key k. Hence, false positives are allowed. But false negatives are not allowed because false negative will happen when one of these entries is 0. That cannot happen if key k is there. So this is a Bloom filter, and it's obvious that as I keep on adding more keys, more and more entries will become 1. It's very hard to remove. In the sense, you can always create a different kind of Bloom filter which has counters, but that seldom serves the purpose. So the entire Bloom filter has to be reset periodically. But this is the broad idea, that false positives are allowed, false negatives are not. And this is a very, very fast data structure, and it is used extensively. All right. So this is the key idea, that false negatives are not allowed. So the Linux kernel uses this reasonably extensively. So the idea of a reverse mapping is like this, that if I get, let's say, some page frame number has to be removed from memory. It has to be evicted. So I go to its struct page. From the struct page, I want an entry of the page table entries, a list of page table entries across processes that point to this. So let us first look at a bad idea. A bad idea is that inside a struct page, you maintain a linked list of all the page table entries that point to this across processes. So the reason that this is a bad idea is basically because, you don't know how large this linked list is going to be, right? In the sense that there could be a lot of sharing. If there is a lot of sharing, it's going to be hard. Second, it is possible, given the fact that we share things at a folio level, it is possible that every page in the folio has exactly the same structure of the linked list. Because let's say 10 processes share a folio, then for every physical page, you will have 10 nodes in the linked list. There will be different nodes, but the structure of the linked list will be the same. So we cannot take advantage of redundancy in this way. So the question is, what do you do? So what you do is to somehow compress information and have a much more intelligent and smarter data structure, where just doing the reverse map is very quick, is extremely quick. And also you want to maintain the minimum amount of information. And if let's say that there is an operation such as a fork, or there is an operation such as a copy on write, you want to do very little work, right? So basically your goals are very clear: space saving, time saving in online operations like a fork or a copy on write, and the fact that you just want to reduce the effort yet maintain efficiency. So what we would like to do is we would like to divide the problem, partition the problem into two parts, right? And then we will solve the two parts separately and combine the solutions. So what we have realized is that having a linked list is not a great idea, because storing those linked lists and they are being stored in kernel memory, etc., is hard. And the thing is that what do you do if there is a fork? So if there is a fork, then basically you will have to add, you'll have to go there, add an extra entry, right? And then if there's a copy on write, you'll have to go there and then remove an entry. That is tough. And also, unbounded size linked lists are not a good idea, especially when better solutions are possible. So given a struct page or a page frame number, same thing, I want to go to a list of VMAs. So what is a VMA? A VMA is a VM area struct. If you would recall, when we were studying about structs and so on in chapter 3, we had looked at a VM area struct. A VM area struct is a region of contiguous virtual memory which has primarily two pointers: a start position and an end position, a starting and an ending. That is what is there in a VMA. And every VMA is associated with an struct, which is ultimately associated with a task struct. Correct? So VMA is a property of the memory map, which is a property of the task, right? It's a property of the memory region. And every VMA is a contiguous virtual address region. It has a start and an end. Correct. So you have partitioned your entire, same way we partition physical memory into zones and sections. The same way the virtual memory space, as we have studied earlier, is partitioned into a sequence of VMAs, virtual memory areas, VM area structs. So the first thing you would like to do is, given a page frame number and a struct page, you would like to go to its VMAs, all right? And then you would locate the VMA. Within a VMA, one of those virtual pages would be mapping to your page frame number. Which one it is, you will solve that. So the first one is problem 1. The second one is problem 2, where given a VMA, you want to do a mapping from the page frame number to the virtual page frame number, right? Physical page frame number to the virtual page frame number, right? So we have two problems, problem 1 and problem 2. We will solve problem 1 first, then we will see the solution to problem 2 is actually very easy, right? Problem 1 will take 10 slides, problem 2 will take 1 slide, right? So this is how we will attempt a solution. And the advantage of going or organizing virtual pages in a VMA is that a common policy can be applied to all, right? And it's much better to organize things. And why do you ever organize? To apply a common policy to a set, right? That's always the main aim. So given that, let us now see what is to be done. So simplest solution, which again will not work, is that I can take a set of physical pages and map them to a VMA. I can always do that. If I go and I map them to a VMA, this may sound reasonable, but the point is that these pages are being shared by multiple VMAs, not one, right? VMAs across processes. So why do I have this? The reason I have this is because one page is being shared by multiple VMAs across processes. So just pointing to one is not good enough. I may point to one, but then that will have a linked list with other VMAs. And then if let's say this thing is forked or something, I need to add more, and this has to be a doubly linked list. So this is not really solving much of a problem. And what if this task dies over here? So what if, let's say, this task here just terminates? Then I'll have to go to every single page and kind of reparent them with a new VMA. So this does not look very elegant, right? The main reason being that whatever I'm pointing to, if let's say that itself changes, that will involve order n work. So because I don't want to do that, instead, let's say that they will map to some kind of a stub, right? So stub is a dummy placeholder, but let them map to some sort of a stub which will remain constant. In that case, what happens is that their mappings in their mapping field, that never has to be changed. Whatever changes will be done within the stub. All right. But let's say that if a million pages are mapping to one VMA, then in this case, they will map to a stub called an Anon VMA, anonymous VMA. And whatever changes are required, I'll do here, but one change here will reflect kind of in all million. It is just that when I'm doing reverse mapping, I'll have to maybe traverse a few more hops, but that is fine. So the stub structure is pointed to by all your physical pages, which are mapping to a VMA. And in this case, they have a pointer to an Anon VMA. All right. Also, the other thing is that VMAs can often get split. They can merge. The task that is owning the VMA may terminate, which all makes the case for mapping them to a stub, which is an Anon VMA. Correct? And processes may also be forked. So a lot of things happen. Because so many things happen, this appears to be a reasonably good solution where this avoids order and work. It avoids going to each struct page and actually visiting them. Correct? So we now will look at the relationship between VMAs and Anon VMAs and see what that relationship will look like. If let's say two VMAs can point to an Anon VMA because when a process is forked, so initially at the beginning, if nothing is shared, a VMA and Anon VMA have a one-to-one correspondence. But when a process is forked, this will become the VMA of the parent. This will become the VMA of your child, right? Same virtual address region, one parent, one child. They will point to the same anonymous VMA. And all your physical pages will point here. Okay? Which means that the parent and child are sharing the full physical address space in this case. That is because there has been no copy on write yet. After a copy on write, the situation will change. But prior to that, parent set, child set are all mapping to the same. So two VMAs are mapping to an Anon VMA. Now consider the other case where a page belonging to a child process is written to. You write to it. When you write to it, the copy on write action sets in. So what happens? A new copy is created. this is associated with a new, so it cannot be associated with the previous Anon VMA. It has to be associated with a new Anon VMA, right? So basically, if I look at a single process, let's say that this is a child process. The child process for a given virtual address region had one VMA. It is now associated with two Anon VMAs. It is associated with one Anon VMA, which is the Anon VMA of its parent. Correct? It is associated with one more Anon VMA, which is the Anon VMA of itself, which is the child. And why? What was the need to create this? Well, the need to create this is very clear. The need to create this is because there was a copy on write and the child did the write. So, fresh copy was needed. So, that is why we allocated a new page and we had to make it point to an Anon VMA. And this has to be the child's Anon VMA. Correct? So, what do we have here? The child's VMA is now pointing to two Anon VMAs. One was the parents and one is itself. And itself can initially be empty, in the sense no physical page is pointing to it. But as you do this copy on writes, more and more and more physical pages will start pointing to the child's Anon VMA. Alright. So we see that there is a complex picture is forming where we have a many-to-many mapping between VMAs and Anon VMAs. Because many-to-one and one-to-many becomes many-to-many. Correct? So that is why I need to further simplify the situation. So when you have many-to-many and one-to-many, what you do is that, and this is a standard computer science thing, it's not a Linux thing, that whenever many-to-many and one-to-many is like a graph kind of situation, right? And one-to-many is like a tree kind of thing. So, for many graph algorithms, what do? Like DFS or BFS or minimum spanning tree? They try to overlay some sort of a tree on a graph. And they could very well be multiple trees. In the case of DFS, whatever node you are starting from is a new tree. So, you look at it, kind of look at it this way, that between a VMA and an Anon VMA, let us create a connector node. Okay. So, the connector node is known as an Anon VMA chain. Why it's called a chain, it will become clear very soon. Let's just call it AVC, short form for Anon VMA chain, where the structure is like this, that every VMA will have a private Anon VMA. Okay. So, let us say that I am a parent process, child process, whatever. I am a process, I have a VMA. Corresponding to that VMA, I have an Anon VMA, which is my private. So that is why my VMA can afford to have a direct pointer to my Anon VMA. But the fact is that I may be associated with a bunch of other Anon VMs. So I will be associated with them via a linking node. And just to maintain consistency, I will also have a linking node between me and my private VMA. Right? So the idea is Anon VMA chain establishes a mapping between one VMA and one Anon VMA on two sides. Right? The Anon VMA is basically kind of one-to-one here, one-to-one here. So, sorry, an Anon VMA chain. And AVC is establishes a one-to-one correspondence on both sides. Alright? It's like a link. And as I said that there is also a link between a VMA and its private Anon VMA, as we shall see, to maintain consistency and also to make the data structures look easier. Alright. So now if I look at the situation of why it's called a chain, let us try to understand. So this part of the diagram we have seen earlier. This we have seen, which we have seen over here, right? VMA to AVC to Anon VMA. So what happens is that this is the VMA of a child. This is the private Anon VMA of the child, where all the pages that the child has created, either fresh or via a copy on write, those pages point here. So these are pages which are exclusive to the child. need not be exclusive, but they are the ones that the child created, right? Fresh. It was not inherited from anywhere. It was something that the child created. They are in this Anon VMA. And as I said, to maintain consistency, a VMA is connected to its private Anon VMA via an AVC node. Now, here lies the brilliant idea. Because of this many-to-many relationship, just let's kindly read this. Different sets of physical memory pages can be associated with the same VMA. Why? Because we have already seen the example where I inherited all the pages from my parent, but I did a copy on write. Then what will happen is that copy on write page is mine. The rest all are inherited. Maybe my parent inherited something from my grandparent. So then I need a connection with my own private Anon VMA. I need a connection with my grandparents Anon VMA as well if my parent inherited something. Because it is possible that there is some page here which points to my grandparents Anon VMA. Subsequently, my parent didn't create a new copy and I didn't create a new copy. So I, as a child, I am actually using my grandparents' page. Correct? Very much possible. So for whatever Anon VMAs are there, all of them are connected to the child's VMA via an AVC. Alright, and the reason it's called a chain is very clear because all these AVCs for a single process are arranged as a linked list. Alright, so which basically means that if I am a child process, I will be, and if I consider a VMA which is a contiguous virtual memory region, the physical pages that actually correspond to these virtual addresses could either be something that I as a child created, could be something that was inherited from my parent, could be something that was inherited from my grandparent or grandparents' parent and so on and so forth. All of those connections will be established via an AVC, where an AVC connects a VMA and an Anon VMA, right? So far so good. And the main idea here is that all of these AVCs are connected as a chain. Is that clear? So far so good. So this is what I do. And the other thing is that, so this is one side of the many-to-many. Let us look at the other side. Consider the fact that a process is actually forked multiple times. So what we have seen is that the VMAs of the child processes still need to be connected with the Anon VMAs of the parent, right? Why is that required? Well, the reason it is required is that consider a page that is pointing to this Anon VMA. Now, let's say this page is being removed from memory. I need to locate all the VMAs across processes where this page is being mapped to, such that I can go to all of those places and repair the state. So how do I do that? I am going to an Anon VMA, right? My Anon VMA is a part of some process, I don't care. That has a pointer to a red-black tree. The red-black tree stores a list of all the AVCs. AVCs, mind you, are just connectors. Okay, AVCs are just connectors. It stores a list of all the AVCs across processes that actually this page is being mapped to. So an AVC does what? It connects an Anon VMA and a VMA. So if I just have a pointer to an AVC, it is good enough, because the AVC will then connect it to a VMA and that VMA will be in some process, I don't care. So the reverse mapping process is like this, that given a page, every page points to an Anon VMA. Every Anon VMA points to a red-black tree. I go to the root of that red-black tree. The red-black tree will have a tree of AVCs. These AVCs are distributed across processes. I go and visit each one of those AVCs. Every AVC on one hand is connected to an Anon VMA on the other hand, is directly or indirectly connected to another VMA. Correct? I will go and visit all of those VMAs, and to every VMA, I will tell that look, this page with page frame number P is being evicted. If you have mapped any of your virtual addresses to this page, kindly invalidate. All right. So there are two. So this diagram is across processes. This diagram is within the same process, right? Within the same memory space. And so this is where a linked list is used, and this is where a tree is used. So now we will combine. We'll combine both these pictures. So let us now look at reverse mapping in the context of an example. So assume we have a process. It forks a child process. So this is the parent process. It has a VMA. And assume that this parent does not have any other parent. So then what will happen is that it will have its private Anon VMA. So all the pages that this parent has created, they will point to this Anon VMA. All right. After a fork operation, pretty much the entire memory space will be copied. But we already know that it is not a physical copy. The maps, they are the ones that are copied. So what will get copied is that for every virtual address region over here, which is a VMA, another virtual address region, which is a VMA, will be created over here. All right. But there is going to be a small difference. The small difference is that the physical pages are now shared between the parent and the child, because the child has not written to any physical page yet. Once a child makes a write, then we will see, then there will be a copy on write kind of situation. But otherwise, what you do is that the child's VMA is attached to the parent's VMA, such that all the physical pages now basically point to the parent's VMA as well as the child's VMA. How is this connection established? The connection is established by creating an AVC that connects the parent's Anon VMA to the child's VMA, and a red-black tree, which this Anon VMA points to, contains the AVC of both the parent and the AVC of the child, such that if, let's say, this page is evicted from memory, via the red-black tree we can reach this AVC and this VMA, and this AVC and this VMA, and then appropriate changes in the virtual memory map can be done. Now, given the fact that the child is a new process, the child will have its private Anon VMA and an AVC connecting them. That part of the diagram is shown over here, where the child will have its own Anon VMA and AVC. Initially, no physical page will point to this Anon VMA, right? So initially, because everything is being inherited, the connections will happen via this way. You can clearly see the red-black tree here. Of course, there is a red-black tree for the child, but I am not showing it. So, I am not showing all the connections in this diagram. Now, there is a page which is pointing to the parent process, which means that at the time of forking, this was given to the child, but of course, a separate copy was not created. The same copy is being used by both using this mechanism. Now, assume that there is a copy on write. If there is a copy on write, then a new page will be created for the same virtual address, and this new page will point to the Anon VMA of the child. All right, which means that if this new page is evicted, it will go to this Anon VMA. This Anon VMA will have another red-black tree like that. It will figure out that there is an AVC, and then there is a single VMA attached to it, which is the child, and appropriate changes will be made. So this is how we manage forking and we manage copy on write. Let us now assume that the child gets forked. If the child gets forked, so first kindly remember this part of the diagram. So this part of the diagram is something that I am copying over here. But because the child is forked and this is the child, all the structures that you are seeing over here, which are basically all of these structures, they will be copied to the grandchild and something additional will be added. So let us see what is happening to the grandchild. So the advantage of this mechanism is that when the fork is created, the changes are made to the child process, nothing is made to the parent. So in this case, a fork is being created and a grandchild is being created. So grandchild will again have the same list of VMAs, but for the same virtual memory region or VMA in the grandchild, now there will be 3 sources, not 2 but 3 sources. What are the 3 sources? One source is sources that are private to the grandchild, pages that are private to the grandchild. That is why it will have its dedicated private Anon VMA and a connection to it for pages that the grandchild creates. Alright. Then it will inherit pages from the child and from the parent. So let's call them parent, child, and grandchild. Alright. So that's what we'll call them, parent, child, and grandchild. So we will call them with this terminology. So the grandchild will inherit pages from the parent as well as the child, which means that it needs 2 AVC connections. One AVC connection it needs to basically the child process, where the child process will have its private AVC and the AVC of the grandchild, both of them will be in the same red-black tree as you can see over here. Alright, such that because any page which is pointing over here is shared with the child and with the grandchild, not with the parent. That means if this is evicted, 2 VMAs have to be contacted. One is this VMA and one is this VMA. And this will happen via this red-black tree over here whose root is here. Clear? Now another connection has to be made, which is a connection with the parent, where the grandchild's grandparent. In this case, there will be another AVC which points of course to the VMA of the grandchild, and it is attached to the Anon VMA of the parent. The reason is that there will be some pages that it will inherit from the parent, the grandchild will inherit from the parent. That is why it needs to create an AVC. So in this case, the entire thing is a red-black tree, which means this entire thing is actually a red-black tree. Alright. The red-black tree in this case has 3 nodes, which are the 3 AVCs. One AVC points to the VMA of the parent. One AVC points to the VMA of the child. One AVC points to the VMA of the grandchild. So basically, as you can see, a reasonably complex structure can form if, let's say, the grandchild gets forked, so on and so forth. But the idea you can get that for a single VMA, there can be multiple sources, which is why you create multiple AVCs for these connections. And for a single Anon VMA, it could be mapped to many different VMAs. So all the VMAs it is mapped to have one AVC per VMA and arrange all of these AVCs as a red-black tree, right? And so then your reverse mapping can be done quite easily, because if something is mapped here, you can easily find all the VMAs that may have a mapping. You will go there and you will do the cleanup. So this, in short, was the reverse mapping process.
We are not fully done yet. We have simply located the VMAs but given a physical address, which let's interpret as the page frame number. We need to go to the virtual page frame number, and this part is not done yet. So assume that the VMA has capital N pages. So then given a physical PFN, this translation has to be done. But mind you, the page table converts virtual to physical, not the other way. So a brute force solution is that we look at all N entries. So this is, we look at all of them and then we try to translate each one of them and try to match, but that is a bit too much of brute force. So an order n time linear search is clearly not practical. We need a constant time solution. We need a theta 1 time solution. That is what we need. So let's look at the idea. So the idea is that the first time a page is allocated, it will be allocated to a process and it will be allocated within some virtual memory region, a VMA of the process. We clearly know that all the virtual pages in this VMA are contiguous in the virtual address space. Out of that, page number I is being allocated and a struct page is being created, and some physical frame number is being associated with page number I, and this association is being recorded in the page table. So we can always store this number I, which is nothing but its offset from the beginning, in the index field of struct page. So we can say that the struct page in its original VMA was actually the ith page in its VMA. This information can be stored, which means that subsequently, if this page needs to be evicted, the number I, which is stored in the internal variable index, this is readily available. If this is readily available, then we can always go to its original VMA, and in the original VMA we can add I to the starting address. So the starting address plus I will provide the address, the virtual page address of the virtual page that is mapped to this struct page. So this is easy, and you can see this is a constant time solution. So there is no need for any iteration or anything. Everything is possible to do in absolutely constant time. The reason being that the number I, which is the index, is being stored within struct page, and the index is being used to find the virtual address at least within its parent VMA, because there is a straightforward correspondence. The fact is that on a forking operation, a VMA can get copied. It can get merged with another VMA and you can have a larger VMA where the entire thing is contiguous. It can be moved in the sense this entire set of virtual addresses, which are let's say 100 to 200 in one process, can easily be made 400 to 500 in another process. So it can be split also. A lot of changes can happen, right? Both in the original process as well as in subsequent child processes. Hence, there is a need for a slightly nuanced solution where the basic idea is the same, but we will make some small changes. So let us say that the parent process has starts at start 1 and VMA1 is the original process, and let's say its offset was I, its index is I. Then clearly for the parent process, we know it is start 1 plus I. But now assume that this VMA gets forked and it gets copied to a child, and after the forking, its starting address is start 2, and start 2 points to the beginning of the VMA. And in this case, clearly the offsets that it was storing was from 0 to n minus 1 because it had n pages. So you can say that the first index over here was an offset of 0 and the last one was n minus 1. We can do it that way. But what can happen is that maybe this VMA over here is some subset of this, maybe let's say this part. Then the offsets will be from A to B, right? So where the offset is with respect to this original VMA, which is VMA1. In that case, we need to compute the address correctly. Where VMA2 is guaranteed to be a contiguous region, in this case, it's a subset of VMA1. But in general, it need not be. It can be a superset or it can be overlapping also. For the general case, we need to find the virtual page address. So let us consider an example. Assume that the parent VMA started at address 1000 and then it had 100 entries. So then the offsets would be from 0 to 99. Now assume that this VMA was copied to a child process, but the child decides to, let's say, move it, shift it to the starting address 2000 and store the offsets from 20 to 50, which means that the virtual addresses in this range are actually stored, and they very well may be mapping to the same physical pages, in the sense this mapping here, this mapping here, right? Same physical page, this is possible. But clearly the entire virtual address space in this VMA is not being used in the child VMA, which is VMA2. So what does this mean? This means that the address range 1020 to 1050, which is nothing but this range, corresponds to the address range of 2000 to 2030, because there are 30 over here. And then what we want to do is that we want to establish a correspondence between an entry here and an entry here, an entry here and an entry here. This is easy to do with simple arithmetic because you see that the sizes of the regions are the same. So we can have a very simple formula mainly based on arithmetic principles. The virtual address is nothing but the starting address of the VMA. For example, it is 2000 plus the index. In this case, let us say the index, which will be in this offset range, let us say it is 40. So let's say this is 2000 plus 40 minus the starting offset, which in this case is 20. So the address is nothing but 2020. So this is very clear that any offset, let us say this is, let's say, offset number 40, it is 20 away from the beginning. Now if the beginning is mapped to this point, then 20 away from over here is here, which is nothing but 2020. So as you can see that just because this index field is stored, we can go to any VMA, which could be the original parent VMA or any child VMA which has copied it using a fork operation and subsequently either shrunk it or extended it. So as long as these offsets are maintained correctly, and note that these offsets are relative to the original parent VMA, so where you are assuming that this was from 0 to n or 0 to 99, if it is relative to that, we can quickly use this formula over here and find out the address of the virtual page. So what is the entire reverse mapping process now? Well, the process is very simple, that we find the struct page. From the struct page, we go to the Anon VMA. So we first find the PFN. From the PFN, we find the struct page. Then we go to the Anon VMA. And then we go to the list of VMAs via the red-black tree that may contain the page. For every VMA, we use this aforementioned equation where we retrieve the index from the struct page and use it to find the virtual address of the page, the virtual page frame number. So there is one question that we have not answered, which we will answer uh, in due course of time in the next few slides actually, which is what we store exactly in the red-black tree. But prior to that, let us appreciate what is happening. Let us clear off the ink and let us see if we can explain this in another way. So the idea is quite simple, that in the original VMA, which starts at some address, we simply look at the offsets with respect to the beginning, the index with respect to the beginning. So obviously the beginning is 0 and the last point would be n minus 1. If this is copied, let us say that you decide to extend it in this direction. That is all right. Then the starting offset may very well be minus 10, which means that this 0 over here would be the same, would correspond to the same virtual address as this, and they would map to the same physical address. So that is why these offsets are maintained and the starting address is maintained. And all that we do over here is that if we need to find the virtual address of the page, then we see where does this VMA start at, what is the index that is stored in struct page, and what does this starting address, which offset does it correspond to. So we subtract that and simple mathematics leads us to the answer. So the last question is that why use a red-black tree instead of an array? Well, the question is that a red-black tree stores a list of keys and values. So it's essentially a key value store in a certain sense. where the value is the AVC. So the AVC is stored. The key is something that we use to do a search and arrive at the values. So we basically index the red black tree. The key is the index. So that is what we retrieve from the struct page. So the key is the index. And every node stores the range of offsets that it stores. So which is essentially, think of it as an index range, that if the index is, let's say, 12, and let's say that this AVC over here corresponds from 10 to 30, then you know that this should be presented to it. But again, if this stores, let's say, some other range, let's say, this AVC, for instance, stores some other range, 80 to 90. There is no point sending 12 here. We can skip this. Let's say we can skip this, we can skip this. So only that part of the tree that has the relevant offsets corresponding to the index, in the sense the index needs to fall within the range, only those AVCs are searched. So this reduces search time and effort and also minimizes wasted work, which is why a red black tree is used.
So now that we have seen the reverse mapping process, in the next lecture, we will look at the MGLRU algorithm.